The Bayes estimator. The Bayes estimator. Sometimes before looking at a sample, we or experts of the application may have some prior information on the possible value range that a parameter theta may take. This information is quite useful and should be used especially when the sample is small. The prior information does not tell us exactly what the parameter value is, otherwise we would not need the sample. And we model this uncertainty by viewing theta as a random variable and by defining a prior density for it, P of theta. For example, let us say we are told that theta is approximately normal and with 90% confidence. Theta lies between 5 and 9, symmetrically around 7. Then we can write P of theta to be normal with mean 7, and because the probability that theta minus mu divided by rho, which is between minus 1.64 and 1.64, such kind of probability is equals to 0.9. In other words, the probability of mu minus 1.64 rho, which is less than theta, which is less than mu plus 1.64 rho, which is equals to 0.9. We take 1.64 rho equals to 2 and use rho equals to 2 divided by 1.64. We can thus assume that the P of theta is approximately equals to the normal distribution, the Gaussian distributions of 7 and 2 divided 1.64, then to the square. So the prior density, P of theta, tells us the likely values that theta may take before looking at the sample. We combine this with what the sample data tells us, namely the likelihood density, the probability of x conditioning on theta, using Bayes' rule, and get the posterior density of theta, which tells us the likely theta values after looking at the example. The probability of theta conditioning on x is equals to the probability of x conditioning on theta times the probability of theta divided by the probability of x, which is equals to the probability of x conditioning on theta times the probability of theta divided by the integration of the probability of x conditioning on theta prime times the probability of theta prime times d theta prime. So for estimating the density at x, we have the probability of x conditioning on x, little x conditioning on x, which is equals to the integrations of the probability of x theta, little x theta conditioning on x, d theta, and which is equals to the integrations of the probability of little x conditioning on theta x times the probability of theta conditioning on x, d theta. Which is equals to the integrations of the probability of x conditioning on theta times the probability of theta conditioning on x, d theta. So the probability of a little x conditioning on theta x is equals to the probability of little x conditioning on theta, because once we know theta, the sufficient statistics, we know everything about the distribution. Thus, we are taking an average over predictions using all values of theta weighted by their probabilities. If we are doing a prediction in the form y equals to g of x conditioning on little x conditioning on theta as in regression, then we have y equals to the integrations of g of x little x conditioning on theta times the probability of theta conditioning on x times d theta, such an integration. And evaluating the integrals may be quite difficult, except in cases where the posterior has a nice form. When the full integration is not feasible, we reduce it to a single point. If we can assume that the probability of theta conditioning on x has a narrow peak around its mode, then using the maxima posterior MAP estimate will make the calculator easier. That is, theta MAP maxima a posterior is equals to the argument maxima of P of theta conditioning on x where the maxima is taken among all possible theta. Thus, replacing whole density with a single point, getting rid of the integral, and using as the probability of little x conditioning on x, which is equals to the probability of little x conditioning on theta map, and y map is equals to g of x conditioning on theta map. If we have no prior reason favor some values of theta, then the prior density is flat, and the posterior will have the same form as the likelihood p of x conditioning on theta, and the MAP estimate will be equivalent to the maximum likelihood estimate. Section 4.2, where we have theta ML is equals to argument maxima of p of x conditioning on theta, where the maximum is taken among all possible theta. And another possibility is the Bayes' estimator, which is defined as the expected value of the posterior density. That is, theta Bayes is equals to the expectations of theta conditioning on x, which is equals to the integrations of theta times the probability of theta conditioning on x d theta. Such an integration. And the reason for taking the expected value that the best estimate of a random variable is its mean. Let us say theta is the variable we want to predict with the expectations of theta is equals to mu. It can be shown that if c, a constant value, is our estimate of theta, then the expectations of a theta minus c to the square, such an expectation, is equals to, if we expanded the terms of the square, which is equals to the expectations of theta minus mu plus mu minus c to the square, and we can separate them into the expectations of theta minus mu square plus mu minus c square, because mu and c are constant. Okay, which is minimum if c is taken as mu. In the case of a normal density, the mode is the expected value, and if p of theta conditional on x is normal, then theta Bayes is equals to theta map. As an example, let us suppose x to the t is approximated by n of theta rho square, and theta is approximated by n of mu 0 rho 0 square, where mu 0 rho 0 to the square and rho square are known. The probability of x conditioning on theta is equals to 1 over 2 pi to the n over 2 times rho to the n, then times to the exponential of the following term, minus the summations of x transpose minus theta to the square, summing for all t divided by 2 rho square. And p of theta is equals to 1 over the square root of 2 pi times rho square, rho 0, which is then time with the exponential of minus theta minus mu 0 to the square divided by 2 times rho 0 to the square. It can be shown that the probability of theta conditional on x is normal with the expectations of theta conditional on x, which is equals to n over rho square, then divided by n over rho square plus 1 over rho o square times m, the average, plus 1 over rho o square divided by n over rho square plus 1 over rho o square, then times mu 0. Thus, the Bayes estimator is a weighted average of the prior mean mu 0 and the sample mean m, with weights being inversely proportional to their variances. As the sample size n increases, the Bayes estimate gets closer to the sample average using more information provided by the sample. When rho 0 to the square is small, that is, when we have little prior uncertainty regarding the correct value of theta, or when n is small, our prior guesses mu0 has a higher effect. Note that both MAP and Bayes estimators reduce the whole posterior density to a single point and lose information unless the posterior is unimodal and makes a narrow peak around these points. With computation getting cheaper, we can use a Monte Carlo approach that generates samples from the posterior density. Andrew et al. 2003. There also are approximation methods one can use to evaluate full integral. We are going to discuss Bayesian estimation in more detail in Chapter 14.